Cool. I think we're ready to begin. So hello, everybody. Welcome. My name is Vittorio Romeo. I'm a software engineer and technical trainer at Bloomberg, and I'm joined here with my co-host, John. John, want to say hi?
Hi, everybody.
Cool. So this talk is going to be a little bit different from my usual talks. I generally, like to go deep into metaprogramming stuff and try to push the limits of the language. But I've been working on something different recently, actually for quite a few years now. I've been kind of like rediscovering C++ 11 and 14 as part of a new project that I'm doing with John and a bunch of other people that are helping out, which is a book that is basically going to analyze the impact of 11 and 14 at large scale companies and provide some advice and guidelines on how to use them, the new features effectively in different contexts. So I'm kind of going back to my roots and taking a look at the standards that I used when I actually started learning C++. I started with 11 and try to basically figure out what has been the impact and what have we learned after having used these standards for many years. So it's a bit of backstory. In 2016, I joined Bloomberg as a software engineer. At that point in time, I was working on trading system backends and dealing with infrastructure stuff. It was quite fun. And in 2017, a year later, I noticed that basically there was a gap in the in-house training for C++. We had a lot of good material about C++ 3 and traditional C++, but we were lacking something about 11 and 14. So I already had some experience with those standards. I was quite, adamant to try out and learn the new standards as soon as they came out. So I developed an in-house course. It went quite well. People liked it. Everybody found it quite valuable. And then, I started looking more into the direction of training and, using my C++, mono C++ expertise to bring the company forward in terms of C++ usage and improving productivity, stability, and quality of our software. In 18, this was actually a CppNow in person in Aspen. I'm really sad that we are, I'm happy that we're able to have the conference and I'm happy that we're able to communicate, but it's just not the same. If you haven't been to Aspen to participate at the conference in person, I strongly recommend it. It's a fantastic experience. And even if you can see like these blurry pictures in the background of my slide, it's very nice and green. There's a light, natural light. Very nice scenery, and it's just a beautiful place, and you're able to mingle with people in person, which I really miss, but hopefully things will go back to normal quite soon. Anyway, 2018, I was CppNow, and I was talking to John. We're talking about, the possibility, the idea of taking all the information and the experience that we gathered over the years using 11 and 14 inside and outside of the company, and basically collating that into a book that people who either are new to C++ 11 and 14, people that are doing the switch as we speak, or people that have experience, but they want to have a little bit more in-depth knowledge of how these standards affect development at a large scale, might find very valuable. So we decided to basically write this book together. And I remember that at the time we mentioned it's going to be a book that writes itself. And, that's it was a bit of an optimistic sentence. It's been a few years, progress is going very well, we're almost done, but it's been a very tough and interesting journey. And the journey happened, across the last few years. It was basically, for me, rediscovering C++ 7 and 14, as I've used it in the past, but I haven't really thought deeply about the consequences and the impact that each individual feature might have. I was able to understand why a feature might be useful. I was able to use them effectively, but I never thought about what is the impact in terms of training. What is the impact in terms of, if you introduce this feature in a code base that's being worked on by developers with very different skill levels and new hires that are coming in at a large company. So that was a very interesting process of rediscovering new standards of C++. We contacted and talked to many people in the standards committee. We participated ourselves in the standard committee meetings. And there was a lot of interesting things that you would not think about when using the features, but you actually figure them out when analyzing them. And we're going to see a little bit of examples of that later. 2021, now this is the year that the book will be released. And despite some, setbacks and some deadlines approaching very quickly, I think that everything is fine and we are going to release a book on time, which, it's quite surprising considering that John is one of the authors, but, we're going to make it. In 2021 is going to be the release of this book, which is called Embracing Motorcycle Plus Safety. So without further ado, what is this talk about and what are we going to cover? So the first thing that you might ask is, why are we still talking about 11 and 14 in 2020, actually 2021? So I kind of gave you an idea before, but we're going to talk about this in depth. How 11 and 14 can surprise you today. It's been years, but they still can be surprising and even dangerous if you don't think about it. And how do they differ when you're working on your small project, maybe with a bunch of friends, and when you are at a very large scale corporation that has thousands of engineers? What is the consideration that you have to make when using those standards at scale? We have this concept of safety of a feature, which I'm going to explore a bit. And basically, we categorize features in safe, conditionally safe, and unsafe. Now, we're going to talk about this later, but don't be afraid of, oh, this feature is unsafe, I never should use it, or this feature is safe, it's always good. This categorization is more about what kind of impact can it have in a code base if people are not familiar with the feature, they don't know their pitfalls, they don't know the feature's benefits. So it's more about being aware of what can go wrong. And in general, no feature is unsafe if you're using it properly, but what is the likelihood that you're going to use it properly with basic training? That's what the categorization is about. And then we're going to see an example of this categorization. We're going to take a look at extended threat declarations, which is one of the features we consider unsafe, and see some examples and see why this feature is interesting. Before I start, I want to say I like to keep things interactive. So we're going to have a chat on Zoom. There's also a Q&A panel on Zoom. So at any point in time, feel free to ask a question either in the Q&A panel or chat, and we can discuss. And I think I'm also able to give you permission to speak if you want to, speak up and have a discussion. I might stop you depending on the time constraints, but in general, I'm happy to keep this interactive and have people ask questions while the presentation is going on. So no hesitation in doing that, please. So this thing is quite nice. It's a survey that's been done pretty much every year by the isscpp.org website. And basically this survey tries to analyze, or to sample rather, various usage patterns of C++ in the real world, in the industry, in hobby projects. And one of the questions they ask is, what is the adoption of modern C++? And they phrase it such as, are you able to use 11, 14, or 17 in your projects at work? So in C++ in 2018, you can see that in terms of full C++ 11 adoption, it was pretty good. We are like 83% adoption, but 14 was lagging behind at around 58%. So of all the people that responded to the survey, C++ 11 was quite popular, but 14 was lagging behind. In 2019, you can see 11 stays stable, 14 starts ramping up. So more people are still able to use 14 in 2019, up to 65%. 2020, both go up a bit. We have 90% C++ 11 adoption, 74% C++ 14. And finally, we have a new survey for this year. And we can see that it's kind of like stable. 11 is around 87% and 14, 76%. It's also interesting to take a look at the other ones. You can see 17 is quickly rising. It's around 56, 57%. And 20, which is brand new, is already being used in 20% of the projects. So it's pretty nice to see this kind of adoption of modern standards. So the results might seem good, and they are good. They are positive results. But if you think about it, around 20% of people were not fully using C++ 11 in 2018. So 11 was released 7 years prior to that, and people were still not using it in 2018. So those people, when they finally make the switch, they will experience 11 as something new. They will experience 11 as something that they haven't had prior experience with. And in 2020, 25% of the people were not using C++ 14. So 14 is not a big standard, but there's things in 14 that are quite useful and quite dangerous as well. And it's kind of interesting to see that some people might have their first experience with that in 2020. In terms of sample size, you can see here on the slide, is not that big. We are like 3K people for the first survey, and then in 2021 we had almost 2K people. So if you want a task for yourself after this talk is spread awareness of this survey. Is going to be done every year by icpp.org, and it's nice to get more information. So if you and your colleagues do it, we're going to have even more data. Also, in terms of my own personal experience, it tells me that CS+11 is still a luxury in some places. There are some companies, including our own, that have unfortunately to deal with legacy architectures. For example, machines that are using still Spark processors or IBM machines. It is the minority, and most of the work is being done on modern machines. But there are some projects that have been making the company run for decades, and they are not easy to migrate. And some people might have been working on those projects their entire lives, their entire careers, and they had never had exposure to 11 and 14. So that's something new for them. And also, if you just go like on Reddit, you go on RCPP, you go on Discord servers, and you go on Slack, you will see people still complaining, oh man, I wish I could use CS+11 at work, or I wish I could use CS+14 at work. So they might be a vocal minority, but they still exist, and it's still a problem. So there's a question from Jack. Do you have any insights of adoption rate in different industries or company scales? So I don't think there is that kind of fine-grained distinction in the surveys. Unfortunately, we don't have the data. And I personally don't know of any data set that has that kind of level of detail. It will be really interesting to see. I can tell you anecdotally, which you have to take it with a grain of salt. I can see a lot of resistance, for example, in the game development community for modern C++. Some people have some misconception about what modern C++ is and the way that it can be integrated in a game development code base. Some people are very reluctant to do that. So that might be an interesting thing to think about. And in the finance industry, which I work in, there is a lot of legacy software that has been written for older platforms and architectures, which unfortunately might not be able to use modern C++ until it's migrated. At least that's my personal experience. But we can discuss on Discord later. I'm sure people have a lot of data to share. So another thing that I want to, the point of this slide is some people might have their first 11 and 14 experience now, or maybe 1 year from now. It can be something new to people. But another thing is that even if you have been using 11 and 14 for a while, both time and experience matter. And sometimes the experience that you get in 6 years of using CS+11 will make you discover things that you had no idea about when you started using it back when it was released. So I like this cliche sentence, which is experience is the best teacher. I think that's the case. And I've been using modern C++ since 2012. It's pretty much how I started learning C++. And I've seen that 11 and 14 has become more widely used in production, especially over the past 6 years in my company, and also in companies that, in other companies, talking to other employees and to my friends, I've seen that kind of trend as well. And I've been professionally teaching 11 and 14 since around 4 years. So there are fantastic learning resources. You can find books, videos, training workshops and things like that. But I've noticed that most of them tend to teach about the features as these independent packets of knowledge rather than giving you the experience. And what looks good on paper might not actually work in the real world. There are constraints based on machines, based on people, based on training. So, you can have the best tutorial ever that teaches you what the keyword final means and what it does, but it might fail to convey when is it a good idea to use it and what consequence do you have in using it when you have a large company that relies on your code. So this is the kind of thing that we're trying also to solve with our project, with our book, is to try and convey information about this experience that we had over the course of many years, rather than just describing the feature and what it does on a shallow level. Now, I'm not saying that every resource does that. There are great resources online available today that also do that kind of sharing, but we're trying to do it from the perspective of a large corporation with thousands of engineers. So how can 11 and 14 surprise you today, even if you are like a seasoned C++ programmer and you've been using 11 for 5 years, 6 years? You might be like, yeah, I know everything about 11, right? But there are still cases where it can be surprising. So I have a question for you. It's a bit of a tongue-in-cheek question, but what is the smallest possible change to the core language that you can think of in C++11? So think about like the most insignificant thing that was changed in the core language. Any ideas? No pointer, smaller than that. There's something even smaller than that. Auto, I wouldn't say auto is a small change. I would say auto is a huge change. Using instead of type defs, we're getting close, but it's not the one I'm thinking of. So think about templates and think about creating objects whose type is a nested template. Let's say you have a vector of vectors, or let's say you have a vector of stud complex. So this kind of nested template instantiations. Can you think of anything? Yes, so Alexander got it. It's parsing the double closing angle bracket. So I think this is one of the smallest changes to the core language, this right here. And if you're not aware of it, basically prior to C++11, if you had a nested template type, like a stud vector of a stud vector of int, then when you defined an object of that type, you had to put a space in between the two closing angle brackets, because otherwise the compiler would parse them as a right shift operator. So it was quite annoying, and this is why in C++3 code you often see these spaces in between angle brackets. And even more annoyingly, the compiler knows your intention because it tells you, hey, you probably meant to close a template here, but the standard doesn't allow me to do that. You have to put a space there. So in 11, they actually changed this and they made it so that the compiler can be smarter and figure out, even if there's a space there, from the context, it figures out that this is going to be a double closing angle bracket, right, rather than a stream or a bit shift operator. And even this small change, which just seems like a quality of life syntactical improvement, it can actually have a real impact on code. So did you know that a double closing angle bracket can make a valid C++3 program ill-formed in 11? And it can also silently change a program's behavior. So the same program can be valid both in 03 and 11, but change behavior because of the double closing angle bracket. So here's an example over here. We have this struct called padded buffer. It takes some power of 2 integer as a template parameter. And then in C++3, I was able to say padded buffer of 256 right shift 4 to get a small buffer. And this was completely fine in 03 because there was no ambiguity between the closing angle brackets over here and the bit shift operator in the middle. Of course, this is really easy to fix in 11. What you do is simply put round parentheses between surrounding your expression, and everything is fine. The other example is a little bit more convoluted, but there might be some cases where you have an expression like this one you see over here, like you have S of G of 0, double close angle bracket, colon, colon, C, and then some other stuff. So this is kind of weird, but this expression is valid, but has different meaning in 03 and 11. In 03, this ends up returning 100. In 11, this returns 0. So I think compilers will warn about this if you have the right warning flags. But I still think it's an interesting example on how even the smallest feature you can think of can have surprising consequences in the language. So I'm not saying this is a problem that you will encounter in real code bases. You might. I suspect it's going to be very rare. But the point I'm trying to make is even the smallest thing you can think of can actually surprise you. And this is a theme you'll see quite a lot in C++, especially in modern C++. So I'm not going to spend time on this. You can take a look at this later yourself if you're interested, and you can play the role of the compiler and try to figure out the difference in result value. So this is one example, but in terms of more realistic stuff, there are things like attributes. Attributes are quite nice. They shouldn't affect, the behavior of your code, but there are actual attributes that can make your code ill-formed NDR. And that means that there is no diagnostic required, which means your program will be completely ill-formed and you will not know about it. Just an attribute in the wrong place can cause that. External template. This is often regarded as like something fantastic to improve compilation times and code size because you can avoid extra instantiations, but sometimes it can actually do the opposite. It can end up making compilation time worse and increasing code size, or sometimes it might not do anything at all. So it's another surprise there. Meyer singletons. They are a very easy way of getting safe singletons that are thread safe initialization. But destruction order can still lead to UB if you're not careful with it. For example, if you have a logger that depends on some other singleton, then you can get into pitfalls where the destruction order matters and can probably do issues. Encoding white space within raw string literals. This might be a little bit more common. You might have heard of it, but raw string literals seems like a very nice feature. You just copy paste and embed something in your source code. But if you are actually relying on the white space being spaces or tabs or having a certain amount of indentation and things like that, then it might be broken by your raw string literals. So what I'm trying to say is that almost every feature, no matter how nice and useful it is, it might have a dark side. It might have some pitfalls that you might not be aware of and that you might encounter in the worst possible moment. What about modern C++ at scale? So in terms of large-scale corporations, one of the biggest issues and challenges to face is how do you teach modern C++ effectively? The problem is that when you hire people, like new people, and even when you try to do continuous education for people inside the company already, so for experienced engineers, you have this like huge diversity of skills and seniority and backgrounds, which is a good thing because diversity helps you tackle a problem from multiple different point of views, and that's very positive. But also it provides a huge challenge for teaching, because if you want to teach C++11 to a classroom of 40 people, then where do you start? There might be people that are experienced with C++3. They are very strong knowledge of C++3, and they would learn more quickly by comparing 11 to 3. There might be people that have very strong functional programming experience, and maybe they would understand the variance and optional immediately, but they might have trouble understanding the more C++ meta programming stuff. So it's quite interesting, and it was a very big challenge for me, and I've learned a lot on how to approach these teaching situations over the course of my teaching experience at Bloomberg. Another problem that we have at large corporations that you might not have in other places is the impact of style guides. So, if you have a small corporation, maybe a startup or a bunch of friends working on a hobby project, you can agree within yourselves quite easily what the style should be. And if you find something you don't like or something you want to change, it's not really hard to mutate that style guide and make a decision. But when you have thousands of engineers, consistent style and rules that might sometimes seem, weird, why is this rule the way it is, actually have a huge impact on how the final code is produced and the maintainability and quality of the entire code base. They exist for, to keep it consistent, to help people that are new get on board with the entire company and figure out how this code works. And that's also something really important. And the key here is, how do we decide what C++11 and 14 features should be talked about in these style guides? Should we forbid people from using some of these features at all? Should we warn people about some of these features? So these things are important and they need to be discussed in style guides. So yeah, I talked a little bit about this. There was a lot of diversity in my training. I've had people as young as 21 and as young as 70 plus in the same classroom at the same time. Some people with prior C++ experience, some people without, but maybe with prior Python or JavaScript experience or Java. Some people are really interested in Moralistic. They love learning about it. They're passionate. They want to know about Moralistic. Some people just want to get their job done, and it's totally fine, right? So they don't have the same spark. You have to be able to sell them, hey, this feature is actually useful and makes your job makes you do your job more quickly and more effectively, right? It's not about the novelty. It's about the value that you get. And some people will work on applications. So they don't really care about all the metaprogramming stuff. They don't really care about the improved template syntax and blah, blah, blah. They just want to get their application safe and correct. Some people are library developers at heart. They want to know how to write abstractions. So there's a lot of diversity there. And it's really interesting as a challenge in teaching. In terms of style guides, without repeating myself, I want to add a few points. The first one is that there are some companies that have very fancy and powerful code governance tools. So for example, Google, as mentioned in a lot of their talks, Google employees have mentioned a lot of the talks that they have these very powerful refactoring tools where they can basically say, oh, we discovered this API is pretty bad, so we're just gonna change it to this other API. We click a button and we immediately send over like 200 pull requests in every place where the API was used. So they have tools which are really powerful. They can introspect the entire code bases and make automated changes. I don't want to say trivially, but very easily. Other companies don't have the luxury. They might be getting there. They might be working to have these tools, but many companies, do things quite manually. If you need to change an API, they will need to first deprecate the other one, then find the teams and the people that are using it, potentially talk to these people either in person or via, conference calls or chatting and tell them, look, we're deprecating this thing. Can you make your changes? So these people will have to make the change, wait for the change to be deployed, then remove the deprecated API and so on. So there is a huge cost, not only in terms of time, but also in terms of people and discussing and trying to get agreement on things that it shouldn't be understated. And sometimes some of the features in 11 and 14 can make this kind of like large scale refactoring and changes harder or easier. So that's something we consider also in the book. And the other thing is that I already mentioned how important a style guide is for consistency, discoverability, maintainability of code. But have you ever thought about what is the input to a style guide? Is it just some person that thinks, I know everything. I've been in the industry for 40 years. I'm just going to write my own style guide and everybody follows it. Sometimes that might be the case, and sometimes that might even work, right? But in other cases, what if somebody wants to actually think deeply about every single rule in the style guide and provide a motivation for it? And it is another thing that we are trying to basically solve with this book. We are trying to be as factual as possible and provide as realistic use cases as possible so that people that end up contributing or writing style guides can back up their choices and their rules from, facts that they have seen about usage of features in C++ 7 and 14. So you can think of Embracing Modern C++ Safely, our book, as a possible input to a style guide. Now, let's start talking a little bit about the idea of safety of a feature, which I briefly mentioned before. So I want to reinstate that every feature in C++ is, of course, safe when used correctly. So when we talk about safety, this is kind of like intentionally controversial word that we use to categorize these features. So for us, safety is more the idea of what is the likelihood that a feature is used correctly, especially in a large company where people have different experience. Does the feature have any attractive nuisance? And that's a term I think that John uses a lot. And that term means, is there anything in this feature that makes you really want to do something or attracts you to something which ends up being problematic or a pitfall? So some features have something like that, which are like, oh, it really seems I should be able to do this, but then I cannot do that, or something else happens. What are the advantages of using a feature compared to its risks? Somebody like Jason Turner in the chat mentioned auto. We all love auto. Auto is a great feature. It helps make your code more maintainable, more readable, but also it can completely kill the readability of your code, or it can introduce defects, it can introduce bugs. And, I would never say to somebody, don't use auto because there might be problems. I would rather teach somebody, hey, these are the things that can go wrong when you use auto. These are the risks that you can encounter when you overuse it in terms of readability, but these are all the advantages that you get by using it. So this kind of analysis of pros and cons is something we do a lot in the book. And this is why, for example, auto is a conditionally safe feature, because it has a lot of good sides to it, but also a lot of bad and possible, problematic issues that come with it. And lastly, another thing that contributes to the safety categorization is teachability. So even if this feature might be, relatively safe, and it might solve a very specific problem in a very good way, is it really worth teaching it to a new hires? Is it worth teaching it to an experienced hire? Or should it be only taught to somebody who is trying to solve that particular problem? So there are some very niche features that solve problems that people might not even think about, right? And including them as part of everyday training might be detrimental to the understanding and to the monetary value of the training compared to not including them. So that's also something that we include in our idea of safety. There might be things that are actually relatively safe to use, but they should be limited to some set of eyes that know what they're doing, and they're trying to solve a very niche problem. So that's also another thing that matters. So yeah, this is the quote from our book. We say that the degree of safety of a given feature is the relative likelihood that widespread use of that feature will have positive impact and no adverse effects on a large software company's code base. So this tries to encompass everything I said again. It is not an exact science, of course. It's a bit of an art, and there's a bit of experience involved in there. And it's just a useful metric that we found to help people decide what to teach or to focus on. So you will probably want to teach the safe features as soon as possible, but you might want to think twice about teaching unsafe features or limit the scope of your audience when you do that. That is the point of this categorization. So we have 3 levels. We have the safe level, and the safe level is a feature. It contains features that add considerable value. They are easy to use and hard to misuse. So ubiquitous adoption of those features is productive. Teach them, use them. They are likely to make your code and your company more successful rather than the opposite. Conditionally safe features, these are quite interesting. They can add considerable value, but they are prone to misuse. So we definitely want people to be aware of them. We want people to use them, but we need to have in-depth training and additional care when using them. Auto is a great example. Auto is great. It can really help your code be leaner, more flexible, more generic, but it can also completely make it unreadable or introduce defects. So you need to understand what you're doing very well when you use auto. You need the training. And finally, unsafe. So unsafe features provide value only in the hands of an expert or only in very niche cases, and they are definitely prone to misuse. So I wouldn't teach these as part of a General C++ 11 and 14 course. I would probably just mention them or even not even mention them. I would have separate smaller courses on each unsafe feature explaining their specific use cases, pitfalls, what can go right, what can go wrong. And people who are trying to either get the maximum possible knowledge of 11 and 14 or trying to solve a specific problem can then sign up to those courses and get the information they need without getting confused, in a general 11 and 14 course. Here's an example of a safe feature. I think override is pretty much the safest thing that was added to C++ ever. It's the prime example of a safe feature. What does it do? Well, I'm sure most of you are familiar with it, but if you aren't, basically it's a kind of like contextual keyword. You can place it after the parameter list of a member function as part of a class declaration. And what is going to happen is that the presence of the override keyword ensures that this member function is actually overriding a virtual function in the base class with the same name and the same signature and return value. So this prevents bugs because, if you want to override something, but you make a mistake, a typo, or you screw up the parameter type, then the code will not compile. It will tell you, hey, you meant to override, but you are not actually overriding, which is good. Without the override keyword, it would actually silently hide the base class member function. It makes your code self-explanatory, so it helps readability. I am reading this code for the first time and I see override and I immediately know, okay, this thing is actually, there's actually a base class which has virtual polymorphism involved, and this thing is overriding it. It gives you a lot of context. And there are really no real technical downsides. Like there is no reason not to use override. There is nothing that can go wrong with it. However, even though this feature is like perfect, there is still one minor pitfall. And I think this was suggested by David Sankel back when we were discussing this feature. And it's a very interesting one. Sometimes, you know, if you use this feature very consistently in a company, like you write override all over the place, you start relying on it and you start expecting that everybody does the same, right? So when somebody forgets to put override in a place where they where it should be put, then you might immediately think, okay, that thing is not overriding anything, otherwise override would be there. So you can start being over-reliant on this feature, and if you don't have it, and if you don't have any system that enforces consistent use of it, then it might mislead you into believing that something is not actually overriding a virtual member function. So it's more of a people problem, it's more of a tooling problem. Of course, you can solve this if you have the right procedure where, for example, you can use Clang tidy, or you can use any other static analyzer that forces you to put override wherever it should be put, or you have a style guide that people follow. But again, it's something that only really happens in large scale code bases and in large companies, and it's something that we thought it was really worth mentioning and an example of a pitfall of a safe feature. What about this one? Range-based for loops. We put this as conditionally safe. And it might be a bit surprising because this is just another way of writing a for loop, which is a little bit leaner and nicer than the iterator-based one or index-based one, but it can really cause problems. So take a look at this code. I have this range-based for loop. I want to iterate over the result of this function over here, which is basically going to give me a bind from a keyboard trigger set of getters. And I'm going to call this member function called get combos. It's going to give me some sort of vector that gives me a bunch of combos, and I'm going to do something on it. So this actual code I wrote for a hobby project. I do game development on the side. I'm working on a game called Open Hexagon. And I had this, I wanted to make it possible for people to change key bindings at runtime and basically provide combinations for their keys in the game. And this was part of my code base. And I had this kind of code over here. And just before you ask, this keyboard trigger getters bind ID, open close parents, returns a trigger getter by reference. So nothing special there. So I want to ask you, do you think there is anything wrong with the code above? Do you think there is any issue in the code on this slide? Okay, some people say yes. Okay, I'm seeing a lot of different answers, which is really interesting. Okay, so some people are mentioning lifetime issues and Yosutis, which we're gonna get to. Some people are mentioning binding to temporize. Actually, this code is perfectly fine. This code is totally okay. And the reason why this code is okay is because we are returning this vector over here by value. And if we return the vector of combos by value, then no matter what the lifetime of this thing is going to be extended, and the vector is going to be valid for the entire duration of the range-based for loop. So this code is completely fine. Of course, we need to assume that bind ID exists and this thing exists and everything is valid code. But there is nothing wrong with this code as it is, because we don't have any lifetime issues as we are returning a vector of combos. However, why am I showing you this if it's fine? Well, turns out that I like game development. I like things to go fast, and I like optimizing things. And I was looking at this code and I was like, why are we returning this thing by value? It's a data member. So I'm just going to fix it, and I'm just going to return it by a const reference. I made my change. Everything worked for a while. And then the replace system started to break. Some replace started to be corrupted in my game. I was like, why? I didn't even touch the replace system. Why is it getting broken? So I did what every reasonable person would do, and is like spend 2 hours looking at the replace system and find nothing. And then I was like, maybe I should just use address sanitizer. So I ran the program into address sanitizer, and it was like, oh, there's some issue in the binding system. I was like, what? I didn't even touch that. Then I looked at it and I remember, oh, I put a const reference there. What did I break? And I figured out that just trying to optimize the code by returning this thing by reference, because it was, a data member, the combos were cached over here, actually broke this code over here, which was relying on the fact that this thing was returned by value, and it was extending the lifetime of this temporary by basically doing lifetime extension of PR values. So it was a bit annoying, but it made me realize, hey, everything was fine before. I changed something which I thought was innocent, and then because of the way that range-based for loops are defined, another part of the code which used to work just fine got broken as well. So I want to show this to you as an example of something that is real and happens. And I know about the range-based for loop lifetime issues. I wrote this code and I was aware that it would be fine because I was returning the vector by value. So when I wrote it, I'm like, okay, this is fine because I'm returning by value. Then a few months later, I was optimizing my code and I was like, yeah, this should just be a returning by const reference. What can go wrong, right? So even if you know the issues around lifetime extension and range-based for loop, you can still screw yourself up by doing something that looks innocent. So this is one of the reasons why range-based for loops is called, is part of conditionally safe features. There are a lot of advantages to the feature, but a lot of things that you need to think about. So now I'm a little bit more careful. And if I ever have expressions like this, I think twice about using a range-based for loop without first, binding the expression to some other place. So the main point here, you need a little bit of additional training compared to override. If I teach override, I'm like, this thing is great, use it everywhere. Don't worry about it. If I teach range-based for loops, I want to show these examples. And I want to be like, they are great, but be careful. And somebody mentioned misused. Yeah, fortunately, the standard committee and people that are interested in this feature are working on fixing this issue. There is this paper, P2012, which is fix the range-based for loop. It's a very interesting read, and they're trying to find a new definition for how the range for loop expands so that people can use it without worrying about this kind of issues. Of course, there are some edge cases that would be broken and stuff like that, but take a look at this. It's a very interesting paper. And maybe in the future, I'm optimistic that I will be able to say range-based for loop is now a safe feature. Use it everywhere, hopefully. Finally, an example of an unsafe feature, decal type auto. So decal type auto is something that I use a lot, actually. But then I realized, why do I use it? And when do I use it? I mostly use decal type auto when I'm doing, advanced beta programming libraries or very generic utility functions. And that is not something that's very common, for example, in application projects. If you're doing library development, it might be something that's very common, but for application development, it might not be. And I've misused decal type auto myself. I've seen people misuse it because I was teaching it improperly, and I'm going to give you some examples of that. So first of all, what is decal type auto? Decal type auto is a combination of keywords that was introduced in +14, which allows you to basically deduce either the type of a variable declaration or the return type of a function to the exact type that's being returned from the return expression or the initializer of a variable. So it's never gonna strip away any reference. It's never gonna assume you want to copy or assume you want to reference. It's gonna either be an object or a reference depending on the expression that is being looked at. So it's way more flexible than either returning auto or autoref. Example, I can have this function wrapper over here called log and call. I take an arbitrary function object f by forwarding reference. I do some logging to track how often f is invoked. And then I can return std forward f of f, open close round parenthesis. And then no matter what f returns, then this is going to do the right thing. If f returns an object, this is going to return an object. If f returns a reference, this is going to be returning a reference, preserving any const or volatile or whatever it needs to be preserved. So it can be very useful in generic code. So what I used to do is, I'm teaching auto, everything is fine. Then I'm teaching decal type, everything is fine. And then my idea was just complete this, this section type inference, and I'm gonna also teach decal type auto. That was my train of thought, is to provide a complete overview of type inference. The actual result was that people often misunderstood the nuance of decal type auto, and it was being overused. Because the way they looked at it was, oh, this does everything that auto does and everything that decal type does, but I don't have to do any manual work, and it seems more flexible. So they started using it everywhere. They were like, yeah, why not use it everywhere if you can do anything that the other features can do? So some students actually gave me feedback like this. If decal type auto does everything that auto does and more, why should I use auto? Let me just use decal type auto and the compiler will figure it out, right? And some other students told me, if decal type auto is more flexible, why should I not use it when I'm not sure whether I should use auto or autoref, right? Rather than thinking, I'm just gonna let the compiler do the thinking. But this is not the way the feature is intended to be used. There are issues with this kind of thinking. The first one, of course, is readability. You are gonna hide some details. If you let the compiler do everything that, for you under the hood, then when you're reading code, you also need to do the same procedure in your head to figure out what's happening, which is not what you usually want. The other thing is that decal type auto can actually be unsafe. Sometimes you actually want to make a copy from an expression that returns a reference. Sometimes it might actually be important for lifetime reasons to do that. And if you just use decal type auto everywhere, you might actually return a reference to something that can be dangling or a local variable or something like that. So it's not something that you should use lightly. And finally, another important point, I think this was Tate Gregory that mentioned this idea, which really struck me something very important. She was talking about emplaceback and pushback, and she said, emplaceback can do everything that pushback can do and more. And this is why I teach people to use pushback whenever they can. And what she meant by that is that if you know that emplaceback and pushback are going to have the same effect in your code, then using pushback makes it more obvious to readers that emplaceback was not necessary there, that the extra power that you needed from emplaceback was redundant. So I really like that. And I think that gave me this new definition of simplicity. And simplicity for me now is using the most limited tool that does the job right. So I would not want people to use emplaceback when pushback is as performant. I would want people to use emplaceback when emplaceback provides a benefit. Similarly, I don't want people to use decal type auto when auto solves the problem. And even if you keep following the logic, I don't want people using auto when using int solves the problem, right? So I like that definition a lot. And I think that your code can actually be simpler and nicer if you follow this idea of using the most limited tool for the job. And decal type auto was something that was overused and went against this principle. And I saw some real drawbacks to that. In order to properly use decal type auto, you need to have a solid grasp on type inference and value categories. You need to know the difference between X values, PR values, reference, R value references, forwarding references. You need to be experienced and familiar with both decal type and auto. So I don't want to teach it after that anymore. I want people to get some experience with those things and then teach decal type auto. You should also have some metaprogramming experience like SPINAC, because that's where decal type auto, comes into play. And also, if you replace a long decal type expression with decal type auto, your function might actually stop being SPINAC friendly. There are some edge cases like that which can be quite annoying. Finally, you can use decal type auto in variable position, as I mentioned, but I really didn't find any valid use case for that. So please enlighten me either now or later on Discord if you have a good use case for decal type auto in variable position where it's the tool for the job and it's not just a possible way of doing it. Please let me know, because I tried really hard. I asked a lot of people and I couldn't find any killer example of, decal type auto in a variable position. Here's the vector tool. For me, the only real use cases for decal type auto are as a return type placeholder in a very generic function that is a template. And you still need to compare that against a training return type because you might lose SPINAC friendliness. So this is a far from trivial thing and you need a lot of training for it. This is why we call it unsafe. So it's not inherently causing problems, but misuse will cause a lot of problems. And misuse is easy. So there was a question about the range-based for loop example. You mentioned, is this problem of the lifetime issue specific to the for loop? It's about lifetime extension for temporaries. Yes, you are completely right. So it is not something that's specific to range-based for loop, but this is the part about attractive nuisance I was talking about. Range-based for loops with their terse syntax and their like you don't have to say begin and end anymore. So you don't need the same expression to be available twice in order to refer to it twice and get the begin and end iterator. They make themselves quite prone to people providing temporary expressions because you only need to say it once. So rather than binding the temporary expression to another variable and then calling begin and end, actually people find themselves using the actual expression more often, and that causes more issues. So the feature itself is not really the problem, because the problem is a detail that's being used as part of the definition of the feature, but the feature itself makes it more likely for people to encounter the problem because of that attractive nuisance I mentioned. So that's the important part about range-based for loop. Yeah, some more examples here. So things that are safe, we have attributes, null pointers, static cast, digit separators. I'd love to see somebody misuse digit separators, but maybe I shouldn't have these challenges because some people will find a way. Conditionally safe, we have auto, const expr, R-value references, and then unsafe, we have things like carries dependency, which is it's widely known to be problematic. Final is a bit of a controversial one, but I think it's unsafe, and we can discuss that later. It's a bit of an interesting one. Inline namespaces, this one is also surprising because a lot of people mention this is great for API stability, and things like that. But if you dive deep into it, it might actually be counterproductive in some cases for API stability and API stability. So it's a bit of an interesting one. You can use it to its full effect, but you need to be aware of a lot of pitfalls. And there's a table of the number of features we cover in the book and where we put them. And fortunately, you can see most of the things are safe and conditionally safe, especially in 14, there's there's not that many features to cover. And in 11, we only have 7 unsafe features, and in 14, only 2. So most of the things that were added, feel free to teach them and use them. Feel free to teach them with a little bit of extra, care, but most of them are safe, which is a good measure of how Modern C++ is actually positive overall and not problematic as people might think. So the thing I get out of the safety as a teacher, for me, is my teaching strategy. So for me, I want to teach safe features early and quickly. Most of them are quality of life improvements that are hard to misuse. So trust your students. I know it's unlikely that teaching these things will cause problems, and I know that my students are smart enough to figure out problems on their own and solve them. Conditionally safe features should be taught by building on top of safe knowledge. So they require a little bit more time, more examples, explicitly showing the students how they can backfire, show them actual examples and quiz them, like I did with you for the range-based for loop. Show them that code and ask them, do you think this is a problem? And make them think about it. So this is the way that knowledge gets stuck in their head and it provides good results. And then at the end, at least in my opinion, I would leave a subset of unsafe features for self-contained continuous education courses. So as for example, if I want to teach people about inline namespaces, I would have a short course or presentation, which is going to be library, API, and IDE versionings with inline namespaces, where I'm going to talk about the feature, I'm going to talk about other techniques, what can go wrong, what can go right, and in general, why it would be a good idea or bad idea to use inline namespaces. And I think this strategy works really well. And the categorization of safety helps me figure out, without having to analyze the feature over and over again, what I should do with it, which I think it's important for productivity and teaching. Okay. So any more questions before we go into this short case study on extended friend decorations? Or is everybody good? Also, John, if you want to add something now, I think is a good time.
Okay, so yeah, you've been doing a great job. So there's nothing really for me to say uh, so far. The intent of the book was to try to make it relatively easy for large companies to assess something where the senior managers may have experience with C++ 98 and 03, but might be scared to death about 11 and 14 and really don't understand why we're using this at all, or if they do, don't have really good insight into which features might, if used indiscriminately, might adversely affect the bottom line. So I think Vittorio explained that we're not saying to use or not use anything. And in fact, there was a goal in this book that words like should don't belong in this book. This book is an input to style guide authors. It tries to be the facts, and the only sort of nested subtle opinion is if something is non-controversial and clear and safe, then it's safe. If something requires sufficient explanation, then it's not safe and it's something else. And when things can be in some context used very safely, because that's the process of the company or the process of the organization, something that is considered unsafe might be absolutely widely used. However, there are situations that we know of where using a feature that some would consider safe are not safe. And since it's controversial, it warrants discussion. And then once people have had that discussion and make their decision, they will do whatever makes sense. But it would be irresponsible of the authors of the book to nest something that is potentially dangerous in some context in a way that doesn't call attention to it, especially since there aren't many of them. So it's appropriate that we at least let you know there are issues here. We believe there are issues here, and we have experience where the issues have shown up. That's all I wanted to say, I guess.
Cool. So there was a question from Jason, which is how was final unsafe? I would say let's leave that to the end. There might be a bit of discussion there, but it's an interesting question. And remember this meaning of unsafe. It doesn't mean that final is something that always cause problems, but it can. So that's what's one of the reasons. We can discuss that at the end if we have time, otherwise on Discord, because I think it's going to spark a bit of discussion. So let's take a look at this case study on extended thread declarations as an example of a feature that might have some interesting, bits of knowledge here and there that you might have not known, and just to give you a sneak peek of what you can expect from the book. So this feature, first of all, is a C++11 feature, and basically it extends the usage of the friend keyword in different ways. So prior to C++11, a friend declaration always required something which is called an elaborated type specifier. So if you never heard of that term before, it's basically the syntactical element of C++ that has this form, where you say something like class C or struct S or union U. So when you specify the name of some type, which is a class, struct, or a union, with the class, struct, or union before it, that's an elaborated type specifier. So if you had the struct S over here, you had your struct example, in C++03, you could say friend class S, and this would be, your friend keyword, your elaborated type specifier over here, and this would declare S to be a friend of the struct example. But you could also do it with a non-existent class. So even though this class doesn't exist anywhere else in the program, you are still allowed to say friend class non-existent, and this will declare a new type, which is a class which is named non-existent, and this brand new type would also be a friend of example, which doesn't make much sense because you don't have that type anywhere. So this was one of the weird things about friends in C++03. This restriction also prevented other entities to be designated as friends. So two examples of those are type aliases and type template parameters. Sometimes it might be useful to have these things as friends, but you weren't able to do it because you needed an elaborated type specifier. So as an example, imagine you have something like a type def for your window manager. This might be, if deft, depending on your platform. Maybe if you detect that you're on Linux, this could be a Unix window manager. And then maybe you have your struct example. It has this template parameter T that you use somewhere as part of your implementation. And now maybe you want to make window manager a friend, but you cannot do that in C++3 because it's not a class. It is actually a type alias for some other type. And you don't know it in advance. So this is actually a pretty hard task. It's an impossible task in C++3. Similarly, T is not really a class. It's a template parameter. It's this type name over here called T, this placeholder. So saying friend class T, again, would be an error, and you wouldn't be able to do that in C++3, which is pretty annoying. So another thing in C++3 that's also problematic is that sometimes it can be surprising what friend does. So as an example, imagine you have this struct called S in the global namespace. Then you have a namespace NS. Inside this namespace, you have this class called X3. And then you declare a friend struct S as part of your, of this class declaration. Now, you would expect this S to actually be the one in the global namespace, but it isn't. What you're doing here is you're actually declaring a brand new type called S as part of the namespace NS instead of referring to the struct S that's in the outer one. Again, this is annoying. It's probably not what you intended because S is right here. You don't really want to declare a new one. You just want to friend the previous one. But there was no easy way of doing this in C++03 either because it assumed that the friend would be in the same namespace. That's a reasonable assumption, but sometimes, it might not be. So C++7 friends lift all the aforementioned limitations and fix that surprising use case we saw before. And you can have your struct, you can have your type def or type alias, whatever. You can have your namespace, your template parameter. And then instead of providing an elaborate type specifier, you just specify the friend keyword and then anything that's a type. So you can say friend T, and now your T template parameter is going to be a friend. You can say friend S, and this unambiguously finds the S outside the namespace because it's not declaring a new one. You can say friend S alias, that also works, even though S alias is a type def. You can say friend decal type of 0, that's fine. Decal type of 0 is a type, it evaluates to int, so this also works. And finally, if you try to do something like friend C, where C is something that doesn't exist anywhere else in the program, then this would actually be an error, which is a good thing. It prevents you from making a friend of something that doesn't exist, which is a positive thing about extended friend declarations. However, we categorize this feature as unsafe. Why do we do that? So first of all, friendship, at least in my experience, is often harmful. And if you find yourself having a lot of friends in your code base, then it's a symptom of your design not being very sound rather than, needing that extra access to private members. I'm not saying there are no good use cases for friends. What I'm saying is that in general, I've seen, and I had this confirmed with multiple other people, that using friends a lot is probably a symptom of bad design. So if I had a book about C++3 features, I would put friend itself, the original feature of friend, as an unsafe feature to begin with. Therefore, this is one of the reasons why extended friend declarations are unsafe. The other thing is that it promotes this thing called long distance friendship. We mentioned the example with the namespace, right? Where you have this thing in the other namespace, and then now you can refer to it with the extended friend declarations. Like, sometimes it can be useful, but when you find yourself friending things from different namespaces, then you're starting to couple things that should probably not be coupled together. And this kind of like attractive nuisance again of this feature that allows you to do that so easily might be problematic in large code bases because people might just use it as an escape hatch and see, okay, rather than refactoring my code and having this third component, which both refer to, I'm just going to use friends and friend this thing from two other namespaces away with this other class. The idea about long distance friendship is that, yeah, sure.
Can I just say one thing?
Yeah.
This idea of long distance friendship goes back way a long time. Parnas talked about modularity, and the idea was that you could have a system that had many different subsystems, you could make a change to the subsystem and it wouldn't affect any of the other systems. Long distance friendship destroys modularity. And therefore, one of the design guidelines for modules in C++20 was to make sure, to the best of our ability, that we didn't allow design cycles and we didn't allow friendship across modules. And that we did the best we could with that. It's pretty good. It's not perfect, but I just want, it's certainly embedded in the C++ standard that this is an important design imperative. It's not just a passing opinion.
Yeah, that's pretty much what's on the slide is pretty much what you just said. I think is an important point to make. Having two types X and Y, which live in separate components, which might be very well modules in C++20 world, and having them friend each other, it just destroys the idea of having things in separate components, modularity of a code base. So it's definitely not something that you want to do. However, even if this feature is unsafe, we have seen how it resolves a lot of restrictions in C++03, and also it has this very neat side effect which helps you avoid typos. As I mentioned before, C++03 friend declarations don't really care if the thing you are friending exists or not. If it doesn't exist, it's just going to be a new declaration. However, if you use extended friend declarations consistently, you won't be able to make typos. So as an example here, imagine I have this struct container, then I have my container iterator, and maybe I want the container to be a friend of the container iterator. Maybe it should be the other way around. This is just slideware, but bear with me. And I make a mistake and just say, okay, I'm gonna have a friend class container. So I'm gonna have a type over here. This will compile, and of course, it's not really gonna be a big deal because eventually the compilation will fail when I try to access a private member of this thing. But it's still annoying. Why the compiler would let me write this code? It's obviously wrong, right? If you instead consistently use C++11 extended friend declarations, then any typo you make will be immediately detected when you declare the friend. So, neat little feature. It's helpful. It avoids mistakes and ensures that you get the things right at the first time you do that. There's other interesting use cases that we cover in the book, like type alias customization points, the passkey idiom, which is also makes use of this friend feature. But also CRTP is one that we cover, and I want to show you a little bit of that because it's quite interesting. I like CRTP. I like templates in general. So CRTP is something that's being researched a lot. It stands for Curiously Recurring Template Pattern, and it's basically when you have some code like the one you see on the slide. You're going to have some sort of base class, and this base class has a template placeholder like this type name T over here. And then you have a derived class. It will derive from this base class, and it will pass itself. So it will pass the derived type itself as the template argument to base. So this is kind of weird. It's called Curiously Recurring Template Pattern because of this particular, derive appearing twice. And the reason why you want to do this is so that the base knows who is deriving from it as part of its implementation. These can be useful to implement things like mix-ins or factor out copy-pasted code without having to resort to things like virtual polymorphism or macros or anything like that. This can be a very nice and neat way of composing things. As an example, I remember seeing, I think this pattern, I've seen it in maybe Jonathan Mueller's type-safe libraries to compose strong type defs. So basically you would have your strong type def, and then you can compose it with CRTP mix-ins. So you can say, I'm gonna have the strong type def for, let's say, meters, which is gonna use an int as an underlying type. And I want to enable comparison, addition, subtraction, but I don't want to have division, for example. And then you can enable all those operations by inheriting from the CRTP bases that expose those operators as part of your strong type def. It was really neat and a nice way of implementing those without using macros. Here's an example use case that we use to show this feature. Imagine you want to count the number of instances of a particular type that are active at any point in time. So you're gonna have this class A, you're gonna have the static integer scount, which is your static counter of instances. Then you're gonna have an accessor to obtain it. And then you're gonna increment or decrement in the constructors and destructors. So let's say we want to increment it when we construct A, when we copy it, and when we move it, and we want to decrement it when we destroy A. And then we're going to have a definition of this in the CP file because it's a static integer and it needs some linkage, some place where it lives. Now imagine you do this for a lot of classes, right? You're going to have your class A, class B, class C, and you have all this code repeated where you have to deal with the counter, you have to deal with the type defs, with the definition of the counter, you have to deal with the getter, the addition, subtraction, and so on. So it gets annoying. So what you can do is you can factor out this counter as a mixin and provide an easy way of integrating it into existing types just by deriving from it. So you can factor it out to this instance counter class. It's going to be a template class taking a type name T, where T is going to be, the actual type implementing it. We are going to have the declaration over here, which is going to be the static integer of the counter. And then we're going to have the getter. And we're going to make this protected so that the derived types can actually mutate it on construction and destruction. And now, since this is a template, we can define the counter directly in the header file. So we don't have to care about having to put every individual static counter in its own TU CPP file, which is good for maintainability and avoiding boilerplate. Now you can use it, and you can add your struct A deriving from instance counter of A, and you can add your struct B derived from instance counter of A or B, and then you can, just works. So do you see any issues with this code? Would you pass code review for my code? Yeah, Jason, the wrong derived type, of course. So I made a typo. I did something terrible. I used Control C and Control V. I said struct A derives from instance counter of A, and then I have struct B derived from instance counter of A. So that's annoying. Why is this a problem? It's going to compile, it's going to work, but it's going to do the wrong thing. It's actually going to mutate the instance counter of the A class rather than the B one. We'd like this to not compile. We'd actually like this to be caught at compile time. So how can extended friend declarations help us here? We're going to see that in a second. There's also another issue I want to mention before that, is that if you have a class further down the hierarchy 3, then it could also mess with the counter because the counter is protected. So if I have something like AA deriving from A, then this class over here might actually mess around with the counter if they wanted to. So we'd like to prevent that as well. We just want A itself to be the only one capable of dealing with the counter. And it turns out that extended friends solve both issues. They solve the mistake and the hijacking of the counter at the same time. So what can we do? We can turn s_count from protected to private, and then we can befriend T. And remember that T is the template parameter that represents the derived class. So this is the new thing that is allowed for us to do in C++11. So we're gonna have this instance counter, same as before, and then we friend T over here. And the other important thing is that this S count is private now, not protected anymore. So now, if you attempt to, for example, use instance counter of A derived from B because you made a typo or a copy pasting issue, then the compiler would actually prevent you from doing that because S count is going to be a private member of instance counter and not a protected one. So, and the friend is going to be A, it's not going to be B, so B is not able to mutate it, which is quite nice. And also the other issue, if you have something further down the line, like AA deriving from A, then you'll be able to prevent hijacking the counter from a class that's further down the line and only keep that over here in A. So solves both issues, which is quite neat. And this is kind of like, I never thought about using extended friend declaration with CRTP, but I can see why it can be useful in these cases. And I think it's something I'll consider more in the future. So there was a question, why is CRTP necessary here? Can we manage the counter in instance counter itself? So the benefit of CRTP here is just avoiding some repeated code. You would have to provide a counter and a definition of the counter for each type that wants to use it, which is pretty much annoying, especially if you supply the counter as a library utility. You don't want the counter to be, you don't want people using this counter utility to have to define the static storage for the counter every time. You want them to be as easy as possible. You want them to just derive from it and it does the job. So the CRTP base helps avoid that boilerplate. I'm sure you could find ways to avoid the repetition of incrementing the counter and decrementing the counter in the instance counter as well. Maybe just providing some constructors would be fine here. I have not researched that, so I'm not sure if it's going to be enough or if there are some pitfalls you need to be aware of, with copying, moving, or assignment or stuff like that. But that could also work as well. So you might even make this a little bit even leaner and with less boilerplate than it is already. But the main point here is providing an abstraction which is reusable and doesn't require much effort on the user side.
Vittorio?
Yes.
I just wanted to point out, here's an example where we're using inheritance where there's no virtual destructor or anything like that. We're using structural inheritance, and we're doing it in a very disciplined way. I'm just going to point this out. And we wouldn't want to put final on the base class either, even though there's no virtual anything. And this kind of thing will come up, that by putting final on something, this is a case where we explicitly want to be able to derive from it. But there are other cases where deriving from something will give you the same kind of benefit, even if only temporarily. And we'll talk about that later. This is the curiously recurring template pattern comes up all over the place, and it avoids some of the runtime overhead that isn't needed and allows us for this factoring. And since it comes up all, in many different guises, and we use it at Bloomberg. In fact, we use it for different platforms. We use the curiously recurring template platform to do our own atomics back about 10 years ago before atomics were part of the standard. So it's really just a placeholder for when you're doing this specific pattern. On the other hand, if you were to use the full power of the extended friend capability of C++11, you could quickly get into the situation where you're saying, I want to make that thing over there or something else over there a friend and completely annihilate your modularity. So the reason it's a chapter 3 feature is we want to show you all the great ways to use it, and we'll just tell you them. And then if you want to do something else, you need to think long and hard before you do it. That's why it's a chapter 3 feature.
And to add to that, teachability, again, I think teachability is another major factor in the categorization. I don't want to teach this stuff to an audience which is just learning more C++. I want to teach this stuff to people who sign up for a CRTP course or a friendship course. Like, I don't want this to be some, the last thing I want is to teach new students about friend, because I know they're going to use it everywhere. So I don't want them to know about it until they are ready. Let's put it this way.
Yeah.
Okay, so we mentioned this, we're almost done. So in terms of like concluding and some lessons learned here, I would say that even though 11 and 14 are quite old standards, they are still an open research area, especially when they're being used at a large scale company. And something that we try to capture, but is really hard to quantify, is the human cost of a feature. Case in point was the example with override. If you assume everybody around you is going to use override properly, and then somebody doesn't, and that kind of like screws up your assumption about the code, that's a cost, and it's something that override costs. But how do you quantify it? Categorizing features by safety, in my opinion, can help a lot with devising learning paths. At least it has helped me in doing my job. I know that I can teach safe features, without thinking too much about it. Conditional safe features, they will require some thought, and unsafe features, they will require their own courses. And I said friendship course is quite funny. I think everybody needs a friendship course sometimes. So that's gonna be the title of my course on CRTP. And all features have good use cases and nasty pitfalls. Knowledge is power, and that's what we're trying to give you. We're trying to give you facts. We're trying to give you examples, use cases. And there is a bit of opinion, it's always leaks through with the categorization and some opinion over there. But mostly what we're trying to do is give you facts and objective analysis of these features. So the book, again, is called Embracing Modern C++ Safely. It's been written by me, John. We have other people working with us very closely, like Rostislav Klabnikov or Alizar Meredith. We have Joshua Byrne and many other people that are involved in standardization and experienced C++ developers that have helped a lot in both the research and reviewing phases of the book. It will be out probably Q3 2021 now, a bit of delays, but I swear it's going to be 2021. We have this domain that you can bookmark. Right now, it just redirects to my page. We don't have a website yet, but when it's going to be out, the domain is going to be used. And if you want to follow me on Twitter for updates, this is my handle. I will definitely, spam it everywhere when the book is out. But Twitter, I'll definitely have a tweet there if you are interested in tracking it. So that's pretty much it. We have like 10 minutes. So I'm going to leave this slide on the screen, which shows you all the features we cover and their categorization. So maybe I'll help you, have ideas for some questions to ask. But that's pretty much it. So I think we can have some time to discuss final, and I want to share my thoughts on that. So final being unsafe, there is a lot of analysis in the book, of course, so it will be easier, to have the book in front of me. But off the top of my head, what I can tell you is that final is not bad per se, right? If you know that something should never be inherited from, then you should mark it as final. And that's the point of the feature, right? The problem is, do you really know when something should not be inherited from? Can you always predict it? Are there use cases that you didn't think about where inheriting from your type, even though it might not be designed for inheritance, might actually be a positive case? So for an example of something that should definitely be final, imagine you are writing a type that's a polyfill for some architecture type. Example, you want an int with 128 bits. So int 128. Maybe some platforms have an extension where int 128 is some primitive type that you can use on that platform and it works just fine, but you want your code to be portable. So on other platforms, you provide your own class, which is an int 128. It does the same thing. It does operator overloads, and it's built on top of two 64-bit integers or something like that. Now, since you're providing your own type int 128 on platforms that don't have one, you want this type to behave as closely as possible as the built-in one on platforms that have it. And since you cannot inherit from primitive types, putting final on your custom int 128 is a very good idea because it improves your portability. If somebody tries to derive from it, they will be prevented from doing that. So if they start compiling your code on the real platform that has int 128, or if your platform gets updated and we get int 128 in the standard, then they won't have code that stops working because they didn't inherit from something that can be a fundamental type. So in those cases where you are 100% sure this thing should never be inherited from, example, for portability reasons, then final should be applied. It's actually a mistake not to put final there. But then there's things like, I'm writing a class, maybe it's a container class. It has a bunch of operations and it's quite useful. Most people will use this container class via composition because they just in the container, they want to add some stuff into it. Other people might want to have, let's say, most of the interface of this container, but add some new member functions on it. Or some people might want to hide some member function from it. Or some people might want to slightly change the behavior of some member functions. So in that case, inheriting from this class and then hiding some of the functions by using private and public and using directives and things like that might be a cost-effective way of achieving what you want. There was this common example with Bjarne in one of his books, deriving from vector, and then hiding the square brackets operator to add an assertion for contract checking to check that the index was in range. I am not saying that is the most robust engineering way of doing that. I'm not saying that's the best way of doing it. Using composition will make more sense. But there is a pragmatic advantage of using inheritance in that way, which is you don't have to re-implement the entire interface of the vector. You can just selectively change what you want, and you're going to have the exact same rest of the interfaces exposed, which might cause some issues, with slicing, and if you pass it in interfaces. But if you don't pass it in interfaces, you just use it as a data member, then it's totally fine. And having put final preventively on that type would have prevented this good use case that might not be the most robust ever, but it might be a pragmatic solution to a problem in practice. And this can happen a lot, right? If you use the principle, oh, anything that doesn't have a virtual destructor is going to be final, then some people might find a good use case to inherit from your type, and it might not be possible. Another example is metaprogramming, the empty-based optimization. There is this thing called EBO, where you derive from types that might be empty in order to basically prevent your type from growing in size. And it's a trick that uses inheritance, but not for the is-A relationship. It's purely a trick to optimize memory layout. And now if your type is marked as final, then the person providing the metaprogramming library not only is forced to basically branch on whether something is final or not at compile time and either store it as a data member or as a base class, depending on that, which increases compilation times, but also you might lose the benefit of the empty-based optimization. So in general, I'm not against final. What I'm against is the idea of let's just sprinkle final everywhere. I don't like that. I think that there are some use cases for structural inheritance which might have not predicted it as a library developer, and assuming that your type will never be useful to be inherited from is a bit too pretentious. Some people might find some good use cases for that. So that's my 2 cents on final. Yeah.
I had a couple of things I wanted to add. The environment in which you work is very important. If you have quick access to change things, you could take the approach that I'm going to make everything final until somebody tells me a good reason why it shouldn't be. I don't happen to subscribe to that in any world, but let's say you could do that. But in an environment where you're doing open source work like Bloomberg, that's not possible. So somebody in the outside using Bloomberg's code won't be able to call up and say, hey, we want you to make that not final because we found a use case. So there's that. People like Jonathan Wakely have said specifically that when they're writing utilities, often what you'll do is you'll inherit from something as part of a framework. And if the thing doesn't let you inherit from it, it can't participate in the framework. And in a presentation he was giving with Marshall Clough, both of them confirmed that final is not a good idea in general. It should be used sparingly when it's appropriate. Alistair Meredith is the one who submitted the paper. He works with us. He's on the book. Override and final were part of the same paper. Override is a wonderful thing. Final is a sharp tool. Final was intended to get back the ability to not inherit from a virtual function so that it could be inlined, e.g. during mocking, which itself is an issue. But the point is, Alistair Meredith, who proposed the paper, never intended it to stop people from dealing with classes that are not virtual by nature. Metaprogramming inherits all, frequently, and does so for good reason. And putting final in there is just putting, grit in the gears. So my basic conclusion is, if you're in an environment where there's inertia to making changes, if it's your own code base, it doesn't matter. But if you're in an environment where making changes has inertia, you are just stopping people from doing what they might need to do. A very typical example would be to inherit from something, as Vittorio said, and make a small change as a prototype to see if it works. And by the way, Bjorn Strustrup says when he inherits vector from his capital V vector from std vector, he uses that in production at his company. He told me this a week ago. I mean, for sure, this is something that people do. So to tell them they're not allowed to do it seems inappropriate and excessively nannyistic. And that's my 2 cents on final.
Yeah, just to finish up, from the perspective of hobby game development, I use this library called SFML. Shoutout is a great library, very easy to use and works quite well. And there have been times where I want to take one of their components and just add a little bit extra on top of it. Like they have this sound thing and I want to add a little bit extra features to do some sound processing and stuff like that. And I would be so annoyed if I had to use composition and re-implement the entire interface just so I can add a member function. I'm not saying it's a good solution. I'm not saying that is the most robust solution in terms of engineering because they can update the library and their API can change or something like that. But I just want to get my game done, and if I can inherit from it and add the member function and it just works just fine, I'm not changing the layout, I don't care. Like, well, why
Even as
not?
a prototype.
Let me do it, right? It would
One
be so
last
annoying
thought,
if
real
it actually
quick.
was fun.
I have a theory for a paper. I know that casting is bad. I want to create a new keyword called no cast, and I want to decorate all of my functions so that I can never cast their address to anything else ever, right? Wait a minute. What if I need to cast it? Then what do I do? Call the developer? Because people know they don't do that kind of thing unless they need to do it. And when they need to do it, the last thing they want to do is have to call somebody. So this is I look at final as a version of no cast. And I would propose that we not submit that paper.
Yeah, I'm a bit conflicted, to be honest. I see the value, and sometimes final drives you towards the cleaner solution because you might want to use composition. But in terms of being pragmatic, I can think of many times where just inheriting from something was solve the problem neatly and quickly and without any issue, that I would be upset if I had to do that extra work, which amounted to nothing. That's pretty much it. So there's a comment from Tanner. In my team, we often derive and override functions. Most people would think of as final for unit testing reasons. We derive testable version of classes that override functions for mocking and allow the unit test to inject data where the class would access normal dependencies. Yeah, that's another good point. Even in a virtual hierarchy, even if you think, okay, this is the leaf of the tree, and nobody should inherit from it, and you mark it final, you actually prevent the use case of testing that, which is another reason to think twice about final, even with virtual polymorphism, which is the intended feature. Then there's also the other thing about final, which you can use it on a member function, a virtual member function. And to be fair, like I never found a compelling use case for telling people, look, up to this point in the hierarchy, you can derive from this member function, but then you cannot anymore. I don't know. I never found a compelling use case. And I've tried looking for them. I tried asking again. It's kind of like the decal type auto invariable position. It's there, you can do it, but is it ever a good idea to do that? And I'd be happy to be proven wrong. This book is about facts, it's about experience, about data. I would never claim that the experience of me and the other authors and the other people is the full global experience of the entire humanity. I can claim that it's reasonably diverse and big because there have been so many people with a lot of years of expertise and different backgrounds involved. But please, if you have data points, if you have counterpoints and ideas, we'd love to hear that. And I think we are out of time now, so we can move the discussion to Discord. If you have any other question or comments or just want to chat, I think we can just hang out there for a little bit longer. And I really hope you enjoyed the talk, and stay tuned for the book. Again, you can follow me on Twitter, or you'll probably hear about it when it's released. And I hope you will enjoy the book as well and have a great rest of your day. Thank you.
Bye all.
Cheers. Bye-bye.